All right. Appendix D, we want to look at the second part of this. And to begin with, I want to go back and talk to you. There are a ton of formulas in Appendix D, so I want to know what you need to know for your test and quiz and what I'm going to be giving to you, okay? So if you start on page A24, of course, we have to know from what we were working on the first part of this lesson, you need to know that equivalent in formula box number 1 to be able to convert back and forth between degrees and radians. Also, on the bottom of the page, you've got like conversions between degrees and radians. I'm just going to tell you, you have to know the whole unit circle. I've already given you a copy of the unit circle again, so you need to know the degrees, the radians, the sine, cosine values. Use those to get tangent, secant, cosecant, cotangent values for all of those on the unit circle. But also there on the bottom of page A24, number 3, the formulas that we were using in the first part to solve for the central angle, the radius, and the arc length. Again, you can't find those if you don't know those formulas, so be sure that you have those. Then over on page A26, you need to know the formulas in box number 4 and box number 5. So those were like the definitions of the 6 trig functions in terms of a circle and in terms of a triangle. I've already told you that you need to know the values of the unit circle, so those are there on the bottom of A26 and again over in the middle of A27, but we've already pretty much covered those. Then when you get over to page A28, you need to know box number 6. Those are the reciprocal identities, which we already were using in our first lesson as well. But from that point on, formulas 7 through 18 would be just a little daunting to have to know in a few days. So for formulas 7 through 18, I will give you those formulas as needed for the quiz and for the test. So formulas 7 through 18, I'll give you those as needed for this quiz and this test. Now, as we go on through the year and we don't hit all of them at the same time, where you're trying to shove them all back into your brain at the same time, then yes, I will expect you to learn 2 or 3 of them at the time. So by the end of the year, we know all of them and we have them in our repertoire for the AP exam. But for right now, to try and ask you to cram all that in would be a little overwhelming. So there weren't really a whole lot in the line of examples for what we want to be able to do today, so I'm pulling from the homework problems. But we want to go through and do some simplifies and verifies like we did last year with our trig identities, and then we also want to use them to help us do some solving. So let's start with number 47. For 47, they ask me to verify, let me see the directions say prove the identity. So prove, verify along the same thoughts. So last year when we did this, we had some tools that we used or some steps that were kind of helpful to us. We said watch for Pythagoreans, and the easy way to recognize those was it was like a trig function squared, or especially if it was a trig function squared in a 1. Also, we said if you had fractions, see if you could combine them or break them apart. See if you could take out a greatest common factor or factor if you had a trinomial or that you could factor, or a binomial into a difference of squares or something like that you could factor. If all else fails, we changed everything to terms of sine and cosine. And we said when all else fails just because if there are 2 or 3 ways of doing the problem, that's almost always the longest, hardest way. So we'd rather do that last. Bottom line was do something, because you start working it out and you get several lines down, it all starts falling together and you didn't even see it coming. So at least write something down, try it, do something with it, okay? So 47, we go through and we've got secant minus cosine is equal to tangent times sine. With the proofs, remember that you may only work on one side. So we're going to choose a side. I'm going to choose the left-hand side. I don't have anything squared that's a trig function squared, so no Pythagoreans. I don't have any fractions. I don't have a common factor that I could take out or any other way to factor that. So I don't really have a choice. I'm going to have to change everything to terms of sine and cosine because all else failed. Now I have fractions, so now I have some options. So if I want to combine my fractions, I'm going to get a common denominator and then combine over that common denominator. And then I can start back at the top of my list again. So flashing lights should be going off. 1 minus cosine squared would have to be one of those Pythagoreans, right? Because if it's a trig function squared, we could use a Pythagorean, but if it's in combination with the 1, it's almost always a Pythagorean. So if this were your quiz, then I would have given you the Pythagorean identity, sine squared plus cosine squared is equal to 1. For the test, I'll just give you a list of all of those formulas from 7 through 18, and you'll be choosing the one that would be helpful for you. Remember, with those Pythagorean identities, they're equations, so you can turn them around in any way. Like I could subtract that cosine squared over to the other side. So sine squared is 1 minus cosine squared, or I could have solved for cosine squared as 1 minus sine squared, or I can turn them around several ways. So I could replace 1 minus cosine squared with its Pythagorean identity. Now, when I get here, I might get stuck. And so there was another tool that we utilized. Here's why I might get stuck. I start going through and I say, okay, trig function squared. I have one of those, but if I use it, I'll undo what I just did. So I don't want to do that. Combine or separate fractions. I kind of have one single fraction over one single fraction. There is a way that I could separate that, but it might not be obvious to me. Factor, yeah, nothing to factor. Change everything to terms of sine and cosine, it already is. I don't know what to do. So one other thing that we had said last year that we could do, even though we're not allowed to work on this other side over here, what we can do is we can take our answer and put it down here at the bottom and start working our way up. I'm still on that left-hand side. I'm still only working on one side. I don't have to write tan y sine all the way down here, but you can see I'm not altering that right-hand side. I'm only working on the left. So if I had come down here to the bottom and written that last line, I could say, okay, I know tangent is sine over cosine, and then I have sine. Okay, well maybe I could simplify if I put those together. So sine times sine is sine squared over cosine times 1 is cosine. Oh, hey, that's what I got, sine squared over cosine. And I didn't even see it coming. Okay? So that gives us another tool that we can use. Anytime you get stuck, go down to the bottom, write your answer, and start working your way up from the bottom. So for this, we had mentioned that was there a way to combine or separate fractions? Yeah, I could separate that numerator, but if I didn't happen to see that, then I could catch it this way. All right, look at another one. 51, they ask me to prove that tan 2 theta is equal to 2 tan theta over 1 minus tan squared theta. So tan 2 theta, the formula that would be sitting there for you to use would be tangent x plus y, tangent addition. So if I have 2 theta, that's just theta plus theta, right? So I'm going to put a theta in the place of x, and I'm going to put a theta in the place of y. So let's come over here, theta in the place of x, theta in the place of y, theta in the place of x, theta in the place of y. So in your numerator, what's tangent plus tangent? 2 tangent. In your denominator, what's tangent times tangent? Tangent squared, yes. So I'm going to have 2 tangent in the numerator and 1 minus tangent squared in the denominator, and that's exactly what I was trying to prove. So again, I didn't really even see that one coming. I just started putting stuff in the formula, and it all fell together. The other type of problem that we did with this last year was ones that we would solve the trig equation. All right, so what we mean by that is, like for 65, it says find all the values of x in the interval 0 to 2 pi that justify the equation. So it's the same idea as if they had said solve 2 cosine x minus 1 equals 0 between 0 and 2 pi. If I'm trying to solve a trig equation, I'm going to get x on one side by itself and everything else on the other side, typically with an equation. But in this case, cosine is attached to x, so that means I want to get cosine x on one side by itself, everything else on the other side. So how do I do that? Add 1 and then divide by 2. So now I've got cosine equals 1/2. Now, if you're on a test or a quiz where you've already drawn out the whole unit circle, you can just look at it and see where cosine is equal to 1/2, but otherwise you might prefer to use reference angles as a faster, easier way to do that. So I can say, okay, where's cosine equal to 1/2, and I can come up to where I've just drawn out the first quadrant instead of having to draw out the whole unit circle. And I can say, okay, cosine is my x value, so it's equal to 1/2 right there at pi over 3, right? So that's my reference angle. Then step number 2, this is cosine equals positive 1/2, so I have to think about where is cosine positive, what 2 quadrants? First and fourth. So I'm going to give the first quadrant pi over 3 and the fourth quadrant pi over 3. So first quadrant is pi over 3, but what's fourth quadrant? 5 pi over 3. Now, last year when we were working with inverse trig functions, there were some times that we called that negative pi over 3. Per our directions here, it said give answers between 0 and 2 pi. So this one is between 0 and 2 pi. This one is not. So I would want to write it as 5 pi over 3. But if your directions changed, and they ask you to, instead of giving answers between 0 and 2 pi, maybe you were given answers in a different region that included negative values. Just a reminder that negative pi over 3 is the same thing there. All right, let's look at another one of those solving ones. Let's look at number 66. For 66, we've got 3 cotangent squared x is equal to 1. So again, I'm trying to get the trig function alone by itself. So what do I need to do? Divide by 3. And then take the square root. Now, what happens when I put in a square root? What else do I put in? Plus or minus, right. So I'm going to insert the square root, and I'm going to insert plus or minus. Now, I have not memorized the cotangent values from the unit circle. I think most of us memorize the sine and the cosine values, maybe the tangent values for the first quadrant, or we just use sine and cosine to get those values. So if you hit something that is cotangent, secant, or cosecant, it's usually a good idea to just rewrite it in terms of sine, cosine, or tangent, the 3 we're more familiar with. So if cotangent is equal to 1 over the square root of 3, then tangent would be the reciprocal of that. Tangent would be equal to square root of 3 over 1. And now that looks a little more comfortable for us. So I need a reference angle. Where is tangent equal to square root of 3? All right, and then where is it positive or negative? Because out in front we had plus or minus, right? All of them, yeah, all 4 quadrants. So I'm going to give all 4 quadrant values of pi over 3. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All of those would be solutions. All right, then they'll also give you just kind of some random other things like you see in number 59. For 59, it says if sine x is equal to 1/3 and secant y is equal to 5/4, where x and y lie between 0 and pi over 2, evaluate the expression. Okay, so if I'm in between 0 and pi over 2, what quadrant is that? First. So in the first quadrant, sine, cosine, positives, negatives, what's the deal? All positive. Everything is positive, so I don't have to worry about the signs anyway. All right, so they asked me for number 59 to find sine x plus y. So that's a formula that I would have given you. I would have given you sine x cosine y plus cosine x sine y. All right, sine x was given. It was 1/3, but we're going to need to find the cosine of x. And secant y was given. So I'm going to need to, from that I could find the cosine, but I'm going to need to also find the sine. Because it's 2 different values, x and y, that's 2 different central angles, I need 2 different triangles. So I'm going to come over here and build a triangle with the x information and then build a separate triangle with the y information. So let's start with the x information. Sine is opposite over hypotenuse. So I could say, okay, if this is my angle x, opposite of that is 1, hypotenuse is 3. Then what would I do to find the other side? Pythagorean theorem to find the other side. All right, let's look at the y triangle. If secant is equal to hypotenuse over adjacent, that I could come over here and say the hypotenuse is 5, the adjacent is 4. What's that other side going to be? 3. I don't even need a Pythagorean theorem for that, right? Okay, so now let's come down and figure out the values for the formula. Again, sine x was given. It was 1/3, so we can just slot it in. Now we need cosine y, so that means I've got to come to the y triangle. What's the definition of cosine? Adjacent over hypotenuse. So if I do adjacent over hypotenuse, what am I going to get for cosine y? 4/5. All right, then I need the cosine of x. So I'll come back over to my x triangle this time. What would the cosine of x be? Yes, 2 square roots of 2 over 3. Adjacent over hypotenuse. And then I need sine y, so I'll come back to the y triangle. What would the sine be? 3/5, opposite over hypotenuse. So then we just need to do some fraction simplification. I'm going to go through and multiply, and I have a common denominator, so I can combine over that common denominator. And again, we want to give the exact value here, not the decimal approximation. Now, you'll notice that that whole block, 59 through 64, use those same values, and you're doing 61 tonight, so that'll save you a little bit of time if you utilize the legwork that you've already done up here in that problem. So here is your homework for tonight on A32 and A33.